Okay, so let's get started again. So we were talking about the different elements of the network, everything from buildings to boxes of various sorts and things that connect the boxes, like these things. So if we start to look now at some fundamental definitions of things. So data flow types tells us how we can use a cable or something like this. So when I connect two things with this, now I only have one thing, but when I connect this and then think of we have a computer here. So the data transfer here, can it go in both directions or not? And can it go in both directions simultaneously or not? Okay, so that has to do with data flow types. So the simplest thing one can imagine is this simplex. So simplex means that data only goes in one direction. So in this particular example, we have a computer here, mainframe, and then we have a monitor, and suppose the information or data only goes to the monitor. It's kind of a contrived example here. I think another example is more like TV broadcast. Okay, data goes from the network to the TV, okay, which displays the program. Okay. Now that's not a super interesting. Well, maybe it's interesting. I don't know. But when we talk about when it's duplex instead, we have two types of duplex: half duplex and full duplex. So duplex means that data can. Sorry. Duplex means that data can go in both directions, but then there is the question whether they can meet. They can have full duplex, or the information first has to go in one direction and then in the other direction. And here's typically the medium that decides this, and sometimes it's also the devices at both ends, whether they're capable of this or not. For this device, I happen to know that this cable supports duplex, so data can go in both directions at the same time. I mean, it supports duplex, so data can go in both ways. It also supports full duplex, so data can go in both directions at the same time. And one reason for that is because there are many cables inside of this one. That some cables are used in that direction, some cables in the other direction. This device, however, is a radio device, and that's typically not capable of doing full duplex. So either data is transmitted from the transmitter here, or it's received, not at the same time. Okay, and that again has to do with some physical properties of the channel, or has to do with physics. Rather, we will revisit this a little bit later. Okay, now, so for instance, an example of half duplex would then be Wi-Fi. An example of full duplex would be modern Ethernet, where this represents then modern Ethernet. So suppose you hook up your laptop or whatever here, then the communication between this box and the computer can go at both directions simultaneously. Now, when we talk about the cores, when we draw these type of lines where data can go, we will generally think of them being full duplex if we don't say anything else. Okay, so when you see a line like this, assume it's full duplex if nothing else has been said. Okay, any questions to this? Perhaps not rocket science, but anyways, right? So connection types could either be point-to-point or point-to-multipoint or multipoint to multipoint. So what is the difference here? Well, basically a point-to-point connection is when a transmission from here is heard by a single device. Okay, so here's one point and here's the other point. So point to point. Now, multipoint transmission is when a transmission that goes out of this line here can be picked up by many devices at the same time. Okay, so this is point to multipoint. Okay, so these type of architectures here, when we have a wire, used to be popular. Maybe it's not so popular nowadays. But one way one can think of this would be like a radio transmission. Here, maybe this is an access point, and here we have a number of laptops which are connected to a Wi-Fi network. Then the transmission from the access point will be heard by all, well, maybe not by all laptops, but a number of laptops. So here it's like point to multi-point communications. Okay, going on, network topologies. So here we have 4 topologies. Let's start with this topology here. So suppose we have a number of nodes here, and if we count them, it's 1, 2, 3, 4, 5 nodes. The most connected type of network we can do here is when each node is connected to each other node with a dedicated point-to-point connection. So we see here that node 4 has 4 outgoing cables here, right? Why is it 4? Because the total number of nodes is 5, so it needs to be connected to, in the general case, to if we have n nodes, it needs to be connected to n minus 1 nodes, right? And since we have n nodes, it means that we need n minus 1 times n total connections. But since a connection goes in both ways, we divide this by 2. So this is the number of links we need in a setup like this. Okay. And we see that if n goes large, this becomes basically quadratic in n. So if you now think about the internet, do you think that is a mesh network? How many believes that the internet is a mesh network? Hands up. 1. How many think it's not a mesh network? Hands up. A little bit more. Yeah. Let me say that I don't know how many devices there are on the internet, but say it's a billion. Okay, 10 to the 9. That means 10 to the 18 cables if that was a full mesh network. No. It's not a mesh network. Right? Now, so this is the most extreme case of a fully connected network, right? So it's kind of expensive because we need many cables, but it's also very good because what happens is that if one wants to talk to 5, the data will of course go this way. But if there is a some type of excavator that digs off the fiber cable here, which happens all the time, then this link is lost, but then data could be rerouted through another node and communication can be resumed after a short delay, right? So it's a robust network, but it's also very expensive. Okay. Now, the other extreme network is a star network, where basically this device here in the middle is some type of connecting device. It could be a hub or a switch. Let's not think about what the difference between a hub or a switch is right now. It's basically something that connects the incoming ports with the outgoing ports. And since this is full duplex, it means that whatever goes in here can go out in all other directions. Right? So this is sort of like a center of a star topology. It doesn't look like a star. Maybe it would be a star if we put some devices on the top here also. But it's called a star topology. So how many links do we need here? Well, it's quite simple. We just need n of them. Right? So it's very few cables, if you like, that are needed in here. It grows linearly rather than quadratic. Okay. So what is the problem with this type of network? Okay. Expensive, robust, cheap, and not so robust. right? And why is that? Well, it's because if there is a power outage here, nothing can happen, right? So we have a single point of failure in this network. So it's not so robust. So what is used in practice is, of course, some type of hybrid between, some type of hybrid between a mesh and a star. And we use mesh topologies to build robustness, and we use stars to save, to aggregate somehow information. Okay, so here we have the mesh and the star. And let's look at the bus topology here also. So this used to be a popular one, which is, still very useful inside computers and so forth, but maybe not so much between computers anymore. But let's talk about that anyways. So what we have here is that we have, first of all, we have a common medium here. And we can think of this as a coaxial cable, which we terminate with some suitable things at the end here. And this termination just basically does that the signal which goes here is not bouncing back and forth indefinitely here. It's sort of like it's absorbed at the end. So some electrical termination here. Then some data that goes down here from, so if we want to attach a laptop to this, we essentially drill a hole in the coaxial cable and we tap out some signal here. So we can inject signal and we can receive signal here. So the signal that goes down here goes out into the other laptops like this. Okay, so it's a shared medium like this. Another thing which is still in use, but I guess to some degree is less popular than other topologies, is when we have a ring. And this is different from a bus in the sense that the devices which are used to connect a device, so if we have a laptop or something like that and we want to connect that to the ring, we split the ring and put in a device which separates the incoming and outgoing link. Okay, so there is not an electrical connection straight through the repeater here. It's a device that picks up something that goes into comes in from the left, say, and then decides whether it should go up to this laptop or not, depending on the address, or if it should be passed along the ring. Okay, so some data that needs to go from here to here essentially goes here, and then it goes here, and then the repeater checks whether this information should go up to this laptop, and it decides not to because it's going to this laptop instead. So it basically then just regenerates the signal and sends it along the way around the circle here, the ring. And this repeater then inspects the signal and says, okay, so this is addressed to a laptop which is connected here. And then the data goes up like this, and it's not passed on. Okay, so it goes on here, follows the ring, and then it terminates here. So it never passes on like this. Okay, as opposed to a signal that goes down here, it goes to all devices regardless of destination. So it's heard by all devices like this. Okay, so these rings used to be a popular thing also in local area networks. It's not used so much today, but there's still on a higher abstraction level, in bigger networks, we have these fiber optical rings that goes around the city and things like that. So, questions? No? Okay. So let's continue then, and then talk about different types of networks. And we distinguish between local area networks and wide area networks, which is actually WAN. Was missed out on the slide here. So LANs or WANs? I don't know. WANs. So yeah. LANs or WANs. Okay. So LAN is a local area network, which is typically relatively small in physical size and something that is typically privately owned. So here's an example of a very small local area network. Okay, this is not powered up and I haven't hooked up a device yet, But as soon as I power this thing up and hook up a device here, I have a local area network. And then I can plug in more devices here. It's 5 ports on this, so I can have 5 other computers connected to this, and that's a local area network. I happen to own this device, or actually Chalmers own this device, so it's not owned by a company that sells a service, a communication service. It's something that we typically as customers or companies own for our own purposes. Okay, now this local area network is not very interesting in itself. It needs to be connected to some other, I mean, it could serve a purpose, right? But if we want to connect this with other local area networks somewhere else, maybe I would like to do some web browsing over this, then I need to connect this device to the internet. So it's connected to some other networks, connected to some other network, and some of these networks will be wide area networks. Okay, but let's, maybe I'm going things in ahead. So here is an example of a local area network. Again, we have this bus topology. This used to be the classical Ethernet when it was invented in the 70s, right? They looked like this. They had a coaxial cable, usually yellow, right? For some reason, they liked yellow. It was not mandated that the coaxial cable should be yellow, but many of them were. And then sometimes when you buy this, you get a yellow cable, which I think is a homage to the original Ethernet standard. Anyways, so this is a local area network. A modern network looks something like this, where you have a switch, and then you connect in the different devices to this. So this is a modern switched Ethernet. So here's the switch here, which basically everything that goes in here can go out in any, can go in the other direction to this, but it can also go out in the other ports like this. And it supports full duplex. And basically, if the switch is a smart device that figures out that data that goes into this cable, if it needs to go out in the 5th port here, it goes out only in the 5th port, not in the 4th, 3rd, and 2nd port. Okay, and we will talk much more about that later on in the course, how this could be done, right? But we think of this, the switches and all these cables, and as a local area network, and then we have a number of devices which are connected to this, and we call them hosts. Okay, so a host is some type of user, human-operated equipment typically, which is connected to a network. Okay, so this iPad is a host, my phone is a host, this is not a host. Okay, this is something else. It's an interconnecting device, happens to be an Ethernet switch in this case, right? So this is inside the network, this is outside or on the edge of the network. Okay, now wide area networks, yeah, it's not very exciting here, but basically it's like something which is typically over longer distances and typically owned by companies that sell communication services. So this could be your Telia, Telenor, some other internet company, right? That owns and operates this equipment and then sell access to this services over this network. So it could be, again, a point-to-point, or it could be something where you have a bunch of switches which are much more intricate and expensive, more expensive stuff than this one, but logically perhaps the same, okay? That together with some very fancy fiber optical cables here, complicated high-performance switches, forms a large, physically large network, wide area network. Okay, questions so far? Just stop me, otherwise I'll continue. Okay, so internetworks, what is that? Internetworks or internets is when you connect several networks together. So suppose we have here, now we see why this is a US book. You have the West Coast and East Coast offices, right? So, okay, so here is a Gothenburg and here's Stockholm, right? So let's do this in Sweden. So here we have a company that has two local area networks. So there is the office in Gothenburg and the office in Stockholm. They obviously want to send maybe private data between themselves or some information. So how do we interconnect them? Well, we form a lease agreement with Telia or Telenor or whatever, some service provider, to give us access to their wide area networks. We put in a router here and a router here, and then we have an inter-network. Okay? This inter-network consists of one local area network, one local area network, and one wide area network. These networks are interconnected with routers. Okay. So what is a router? We will talk much more about that later on, but it's something that can interconnect different networks or similar networks, but logically separated networks. So for instance, to make this more concrete, maybe this is the switched Ethernet, right? And then there is a router here, which is like a fiber optical modem, say. And then we have a fiber optical network and a fiber optical modem okay, sorry, I went ahead. So this router here is connected through Ethernet here, but a fiber optical link here. So it's something that connects possibly two different technologies and are able to transmit data, to accept data here, convert it and send it into some other format here. And it could be much more complicated network inside here where you choose different paths and so forth. So we'll talk much more about what the difference is between a router and this device, which is called a switch. Okay. If you Google what is the difference between a router and switch, you will get conflicting information, right? But I'll try to keep a certain terminology in this course, and we'll talk about it later. So don't worry about that at the moment. Okay, a more complicated Ethernet would be, for instance, if we have a single laptop, maybe at the home, we have some type of switched Ethernet, maybe at school, and then another switched network at some company, and we would like to interconnect these things, right? And then we have in the middle a switched WAN, and then we add some other stuff to this, and here we have a little bit more complicated internet. Okay, so we have one network here, we have one network here, one network here, another here, third here, and a fourth here. Right? A bunch of different networks, could be running different technologies and so forth. They're all interconnected by these routers. Okay, questions? Okay, so an internet is basically when you connect several networks together. And the biggest internet we know of is the internet with a capital I. Okay, that's the internet, where we do our webbing and all these things. Okay, but there is a technical term, internet, which basically is when we connect several networks together. So we can have a private internet, for instance. Questions? All right, then we continue. Switching. Okay. So here we start now to become perhaps a little bit more technical. There are two switching types, something called circuit switching and something called packet switching, as we will see later on. So circuit switching, the way I would like to describe this is basically to take an analogy of the old-time way the telephone system was built up. Okay. In the good old days, a telephone was a device which was placed on a table. There was a connection into the wall, right? So it was something that looked like that. You lift up the hook, and you hear something beeping in the hook, and then you dial your number, and then you hear the ringing tones until the other party lifts up the hook, and you can start to talk. Okay, so that's the old classical telephone system. And what I just described are the three phases which are typical, or the first phase which is typical in a circuit switched network. Here, communication consists, or if one wants to communicate between, say, this telephone and this telephone, how is this done? Well, it's done in 3 phases. First of all, there is setup phase, where a path from the initiating node to the receiving node is generated throughout the network. So basically, it's like this: that once the hook is lifted on this telephone, the telephone communicates with the first switch here. Basically says, I would like to communicate. The switch then acknowledges this by sending a dial tone back to the receiver, to the initiating party. The initiating party dials the number, and the number explains to the switch which other phone the initiator would like to talk to. Okay? And then it's up to the switch to figure out a route through the network, and maybe the route is like this. It goes like this to this switch, up to this switch, and then over to this switch here. And then all these switches, you can think of them as electrically connecting the input and output ports with physically connecting, as it was in the early days, right? Then once this connection has been done, the switch at the end sends a ringtone to the other phone. So the person on the other side knows, okay, somebody wants to call me, and that person lifts up the hook. And now we have finished up the setup phase and go over to the information transfer phase, where we start to talk. Talk. And when we're done, one of the parties puts down the hook, essentially say goodbye, and then puts down the hook. And then we go into the third phase, which is the teardown, where this connection is erased. So the switches then release this connection, so it can be used by somebody else. Okay? So simultaneously as this, these 2 phones, this one and this one are talking, so maybe this phone would like to talk to this phone, and then the same procedure happens. It goes to the switch and then gets a dial tone, and then the one presents the telephone number that I would like to be connected to, and then a path through the network is connected. And maybe it goes the same way as the other one, right? Because it can go the same way because the capacity of this line that interconnects the switches is much higher than the capacity from one phone to the switch. So we can have several phone conversations going on over the same cable. Maybe hundreds or thousands, I don't know. Now, if the capacity of this line is exceeded, then maybe the third party here that would like to talk to this one will be routed some other path through the network like this. Okay, but these paths through the network are fixed and does not change during the conversation. They're for the exclusive use of the communicating parties until they're done. Once they're done, these paths are released and can be reused for others. Okay, and it might very well be so that the capacity of this switch is full, right? It can maybe only connect 3 telephones at one single time. So then when the 4th phone tries to call, the network is not able to serve that user, right? So the user is blocked. Okay, so some other things here. The switches here do not store data in this. They only connect the communicating parties. The advantage of a switched circuit switch network here is low and stable latency. And the reason for this is that there is a connection being set up, and this remains in place for the entire communication. So very little things can disturb this communication. The delay will be the same. It will be fairly low. The problem is that once this has been established, a connection, it will be using network resources regardless if there is any communication going on or not. So maybe you call up your friends and then you talk for a few seconds, and then maybe one decides to go and put down some coffee, and then no communication happens until that person comes back with a cup of coffee, and then conversation restarts. For the entire period where there was no communication, the network resources cannot be used for anything else. Okay? So you reserve resources, you use them, or they are reserved regardless if they're used or not. Okay? So this is one problem with this, that we can have potentially low utilization of the network. Okay? And why is this a problem? Well, of course it's a problem because if you want to support communication on many devices, you have to potentially design the network to the peak traffic rather than to the average traffic. So it's could be an expensive solution. Okay. So the other type of switching is packet switching. Okay. And this is what okay, let's talk about what it is first of all. Here, a communicating device, say this device that would like to communicate with this device, does that without this three reserving phase, right? So basically, packets goes from the initiating party or the party that has data to send. It sends it to this closest router. The router gets these packets and place them in a queue. Okay. The router, now this is not a router, but suppose it was a router. Then a packet comes in here and is stored here until it's time to send it further away, right out another port. And then it goes to the router on the other side. It comes in here and stored, and it figures out where to send it next. Maybe it's out through the top port here. I don't know. Okay. So the devices here receives. Okay. The packets comes into the router. It's stored here and then forwarded out to the next jump, to the next hop, to the next router where it's stored, and then forward to the next hop and so forth. Okay. So it's basically a store and forward network. So again, packets are buffered or stored in the routers, and they are forwarded when the output link is available. Okay. So these packets that come here ends up in a queue until the output line is available, and then they're sent over to the next router where they're stored and then output to the receiving end whenever that line is available. Okay. So the first packet here might go this way and then go this way. So this was the first packet. Now, there is nothing that guarantees that the second packet will go the same route. So the second packet in blue here comes and it's placed in the router queue, but then it turns out that this output line here is quite busy, right? There is a lot of traffic here, but this one seems to be available. So then the packet is routed towards this router, which then sends it here and then sends it here, right? So every packet potentially gets its own path through the network. The path is not predefined. It's dynamically allocated depending on how busy the network is and what path seems to be available. Okay. So packets for a given transmitter-receiver pair can go over different network paths. Okay. And for this to work, the packets need to contain addresses. Otherwise, how does this router know where to send it? It has to look at the packet which is in its queue to figure out if it should go out this way or some other way, right? To reach eventually the destination. The advantage of a packet switch network like this is that it gives good utilization of the network links because it's adaptive. It can change the routes depending on the demands. Okay. So it's a little bit like, for instance, if you want to, I don't know, drive to work or something like this. You know there are several paths you can take. Which one do you take? Well, you typically take your normal path, but if the path is congested forward, maybe you make a detour because you know you will get to your destination quicker. So you dynamically use the network, in this case, the road system, to serve your needs in a more efficient way. Okay. Now, a typical example, or if you want to have a mindset of what a typical circuit switch networks is, old-style telephony. If you want to think of a packet switch network, you can think of this as maybe the old-style telegram network, or for instance, when you send a letter in regular snail mail, right? You write your message on a piece of paper, you put it in an envelope, set an address to this, put it into the mailbox, right? And then who knows what path that takes before it receives on the receiving end. It can go through many things. I mean, it could be, on Tuesdays maybe it goes through train, Wednesdays it might go through an airplane, and who knows how it's going to be delivered. Maybe there is a mailman or mail person on a bike or whatever, right? There could be different paths through the network. Questions? Okay. So which one do you think is used in the internet today, of these two things? There are two options. One is right and one is wrong. Packet, right? It's dominated by packet switching, but there is a fair amount of circuit switching also going on, called virtual circuit switching, where there is not the mechanical switching here, but you reserve paths through the network. So actually, there is actually three answers, right? Both of them are used. But for sure, this is a packet network. Okay. We continue. Example of then this packet switching network, if you want to have that in more detail, a telegraph, for instance. You have messages. These are telegrams. They have three parts of it: a receiver address, sender address, and then user message. Just as a regular snail mail, right? You have a message. You put it in the envelope, you write the destination address and the sender address here. And the sender address is because if something goes wrong, the network can inform the sender of what has happened with this letter. And also the receiver can figure out who sent this email from the sender address. There is some message switching at the receiving station. So telegraph network consists of many stations interconnected with lines. So there is an incoming telegram. Somebody looks at the telegram and figures out, okay, you should go out in some other direction. So there's a store and forward thing. So receive, store, determine the next hop, and then forward to the next station. And eventually it reaches the final destination. Messages are multiplexed over these transmission lines. So many messages can go over the transmission line. So again, if we take the snail mail analogy here, many letters goes into the mail truck, right? Okay, so many packets go over in the mail truck. We need framing in these type of systems. We need framing, which is a way to figure out, okay, here's the start and the beginning of a message. We'll talk more about that later on. Circuit switching is this telephone system, old-style telephone system. We have a connection setup, information transfer, and connection release. And basically here is what I earlier said, right? So in the connection setup, we pick up the phone, we get a dial tone, we dial the number, and then the network finds a route, and then call the receiving party. The receiving party picks up. Now the path is established. Then there is information transfer, blah, blah, blah. Connection release is like goodbye, and one hangs up, and then the telephone network releases the connection. Now, a little bit of a quiz here. So, now I ask you the following question. You could just raise your hand. So what is true for the telegraph system? Before the telegram is sent, the route from the end stations is determined. Yes or no? I'll give you 10 seconds to think about that. So how many for yes? How many for no? Okay, so it's actually no, right? The telegram system is that you give the telegram, and it's then sent on to the next station, to the next station, to the next station. It's not that the end stations first say, okay, here comes a telegram, are you ready for this? No, they don't. So you just push in the data into the network, eventually it finds its way, hopefully. Okay, so what is true then for the telephone system? Before the caller can start talking, the route from the end station is determined. Yes or no? I'll give you 5 seconds for that, because you can conclude from the first question what the answer is. Yes. So how many is for yes? Here we go. No? Yeah. So here is the true, right? Here we establish a connection between the end points before any user data can be transmitted. Okay. Consider a system with end stations that would like to communicate. Which topology is the most economical? Mesh or star? Give you 10 more seconds for that. All right. How many for mesh? How many for star? Yeah. So star is the correct answer here. Okay. So this gives you a little bit of a flavor what the quizzes will be later on. It will be this type of questions, maybe slightly more difficult. There will have more choices to choose from. Some of the choices are correct, but there are other things which are more correct, right? So it's like the usual thing, right? I think we will actually, I think I have 2 more minutes. So, okay, so let's do something here. Okay, so let's just do this. So, computer networks, which we will be concerned about in this course, we have these protocols, these mystical protocols that we will start to talk about quite a lot in the following lectures. So these protocols, what are they? They're a set of rules that governs how 2 or more communicating parties should interact. Okay, kind of hard to grasp what this could be. But examples of protocols is the Internet Protocol, IP, the Transmission Control Protocol, TCP, Hypertext Transfer Protocol, HTTP, and Simple Mail Transfer Protocol, SMTP. I don't know about you guys, but I used all of these protocols today. Right? It was not obvious to me, but I have. Right? Communication then between connected computers. Okay. They are done by exchanging packets. Okay, that could also be called messages, segments, or frames. We'll talk about what the difference are between these 2 things, which is basically some data that is the user information. So in my case, when I sent an email, this is the text that I have in the email, and the header here contains the my email address, the email address of the person I would like to talk to, and some other stuff. Right? So that is determined by this simple mail transfer protocol. And then when this data was actually going to the receiving end, it used TCP over IP, I believe, or maybe it's UDP over IP, but for sure, one of these combinations. We'll talk more about this. The header here contains addresses and some other control information. So this notion about packets consisting of a payload, some data, and some control information is quite important. And we will talk much more about that in the coming lectures. But now, I took 1 minute from you guys. So we'll see each other on Thursday. So this week will be quite hectic, right? There are 2 lectures on Thursday back to back. So bring your coffee. I will bring mine. And then we have 1 more on Friday. So it's going to be a jump start. And we need that because I would like you guys to start work on your projects as soon as possible. Okay, see you on Thursday.